Hello, welcome to another video. I just want to give an overview of kind of the other big problem in calculus. So at this point we've been talking about derivatives and thinking about the derivative as kind of an instantaneous rate of change. Okay, and so something's changing, right? We've got water, and then we take mark times. Well, after 1 second it's here, after 2 seconds it's there, after 3 seconds it's there. How quickly is it changing? And when we graph that behavior, we've got some water level and it's falling. We think about kind of the slope at a point, and we approximated it by finding kind of slope between points on the graph and then getting closer and closer and closer until we find out that we can somehow think about, well, if we only moved from x to a little tiny dx over, we could think about kind of an infinitesimal, is how Newton and Leibniz thought about it, change, and measure the change in the function, and then we get this instantaneous rate of change, which we're going to call the derivative. Okay, so that's one of the big problems in thinking about how the world works, is being able to describe how something is changing. And since Galileo kind of brought math into doing science, um, we had these functions. We were describing things with functions, and so we wanted to be able to talk about how did the functions change. And that's what Newton worked out, and then Leibniz after him, when he didn't let people know kind of exactly what he had done, but showed the kinds of problems he could solve with it. Well, the other problem, if we're thinking about things changing, or if we're even thinking about kind of how to describe the world, is how much stuff is there, right? So these problems go back to antiquity, and one of the first people to start doing this kind of thinking was Archimedes, who lived a couple hundred years after Christ in Alexandria, what is now in Egypt. And he was trying to figure out this age-old problem of how much stuff is there in a circle. And it occurred to him that, well, he could approximate a circle with a square. Everybody knows how much area is in a square. Well, but it would be an even better approximation if he doubled the number of sides, if it was an octagon. Or if he doubled the number of sides again, and it was a 16-gon or a hexadecagon, or a 32-gon. And because he was able to figure out the area of these different regular polygons, he realized that he was approaching this single value. Much like when we were thinking about derivatives and we made our approximations closer and closer, it didn't get ridiculous. It didn't vanish. It didn't go to infinity. It approached like a specific number. And that's why Archimedes was able to figure out there's this number pi, which on a circle was the ratio of the circumference to the diameter. That allowed him to figure out that diameter was also connected to the area by the same constant pi. And he was able to work out quite a few digits of pi because he was so good at that kind of approximating calculation. Well, we can think about same sorts of things, right? You've got a fancy beer glass and you want to know how much it holds. There's no formula for something like that, right? It's not a cylinder. But we can imagine, well, what if we cut it up into chunks? Right? We thought about it in a little slice, and then we added up the slices. And our notation for adding things up is, because it goes back to the ancient Greeks, is going to be a sigma, which that's a capital sigma, lowercase sigma, because we're summing up. And if we could somehow add up those slices, each slice is some circle. The whole thing is in a cylinder, but the little slice is pretty close to a cylinder. And the volume of a cylinder is the area of the top times the thickness. Well, how much of a thickness is that? Well, we're going to steal this idea from Newton and Leibniz and say, oh, well, what if it's just a little bit of the height? And then if we imagine that those slices getting thinner and thinner and thinner, that becomes a perfect approximation. Right? So much of calculus is about this idea of we make better and better approximations, and then we're going to think about this kind of where is it going, and that's going to be our thing. Right? So as we get better and better approximations, we're going to shift from the Greek capital S to a long curvy S, and we're going to add up our functions and with just a little bit of change in the variable, and then we're going to call that integration. Right? The integral really refers to the whole, so integration is about finding the whole by adding up lots of little pieces. And so we'll be digging into that more and more over these next couple weeks. So thanks very much. And I actually kept it a little bit quick this time, but we'll see where we go from here. Thanks.